Nesta,
Yeah,
hey, evening.
even.
Sir, did send any notes last week?
No.
Oh, all right.
Um,
Good afternoon, students. How are you doing today?
good evening.
Mhm. So let me apologize. For the past 2 days, I've been having internet issues, and the guys only came today to sort it out. So it took me a while to reset and everything. Um, they left like a couple of minutes ago, so um, apologies for the late start. Shani, are you hearing us this day today? Shani? Daniel, are you with us? Next is just you alone.
I guess so, sir.
All right. You, I have not even logged on into the other device, so just give me half a second. If I give the others a few to come in.
Good evening, everyone.
Shani,
Yes, sir.
how do you pronounce your name?
Shani, you said it right
Okay.
just now.
Okay. Well, I get it right today because I was calling you, and you've never corrected me.
Sir, too much people get it wrong, so I just accept it however it is.
When people call you?
Shani, Shanice.
No, well, I was calling you Shani.
Shani, I've got that too, yeah.
And
But
it was,
I don't really get that a lot.
oh, and then it was, oh goodness, what's your name again?
Ottilie?
Ottilie, oh Jesus.
Mm-hmm.
All right, Ottilie was saying to me, no, sir, her name is Shani. I was like, it's not Shani. So it's by chance I took it. All right, so I need to talk to you off. I need to talk to you off air, Shani, and I mean after class.
Mm-hmm.
But I just want to make a disclaimer.
Yeah.
The truth is, yesterday morning I lost a co-worker of mine, somebody from my department that I directly supervise.
Oh, sorry.
And yeah, man, and it was a tragic accident, and it has been affecting me significantly. I have been suffering from a terrible headache after bawling several times. When I talk about the decent crime, I talk about drop and roll ball. When I heard the news, I've had this terrible headache, and even now as we speak, it's as if somebody is just using a chisel and just chiseling out something. So if I were to say that I'm going to be leaving class, no, I don't want anybody to think that, boy, I'm being irresponsible.
No, sir.
Yeah, it is. You're so quick, you ball out, no, sir.
I just think the same thing. I was just thinking the same thing.
Mister, you're so quick, you don't even say, oh dear sir, how you feeling? No, sir.
I was about to go there.
Never
I
mind,
understand.
mister. Yeah, man.
So
Yeah,
I understand losing somebody, so that's why I said that.
Yeah, we had an encounter just this week. You know, it's really it's not it's not easy. It's really not very easy. And you know, to be honest with you, yes, I would have lost team members before or co-workers before, but not anything as tragic as this, you know. So yeah, so I'm saying this to say to you that I'm still going to be very purposeful in what we did last week. We started and finished a topic. I'm going to see if I can find a past paper question so we can work through at the top of the class, because we are done with that topic. And then I'm going to see if I can start and finish another one and see how best my headspace can take me through. Hold on 1 minute, please. All right, so this other system don't come up yet here. Hold on. Oh Lord. All right, so remember now, this is a very short semester. I intend to see you guys through for the semester, so we can't really we can't really, we have to make sure that we get the things that we're supposed to be getting and getting them from the get-go. So I'm begging you, please, don't lay on me.
Sir, will you be going through the past paper question, or you'll just give it to us and leave?
No, man, for the one for now?
Uh-huh.
Oh, yeah, man. No, man, I want to give it to you to see how. Last week, I was calling upon you, but I recognize you're maybe not, we're not connected to the audio. I don't know what it is, but I don't know if you were hearing me. Were you hearing me last week calling you?
No, because my internet, it was fluctuating, and then I ended up falling asleep because it was just in and out, and I wasn't hearing anything that you
I
were
kind of
saying
figured.
steadily.
I kind of figured.
Yeah.
Because I was calling you several times and couldn't get through to you. Crap.
Yeah, that was
Forgive
it.
me. I did not remember to upload the video. Forgive me. Now that you're saying it, I was about to
Yeah.
ask you if you listened to the video, but I did not upload the video. I'm not one who is going to deny it. If I don't do it, I just never did it. Sorry. I'm gonna
Yeah.
upload that video. I'm gonna upload that video. Oh, God, it's killing me. I'm gonna upload that video. I'm shortly from now, so you can have that. So okay, so what I'll do then is to go through the question with you, so at least you can see what happened. We started and finished Newton Rampson. So we're going to see how best we can do. But just give me half a second. See if we can round up Arthur Lee for me, please, Shani.
She
And
said she said she's coming at 6, sir. She messaged in the group. Why I
oh,
was
she did.
asking if you were going to go through the question is because I'm at work, and if it is that you were just going to give it to us, I would just leave with my coworkers that are leaving now.
Oh, okay. So do you have data on your phone that you can even listen on in transit? Because I wouldn't want your coworkers to leave you. You're getting a ride, that's what it means, are taking the bus.
Well, I work downtown, so we'd walk the parade and then from there take a bus.
Oh, I don't want you.
Yeah.
Are
So
you
you were
still at that
going
place? You still at that place or you change jobs?
I changed jobs.
Oh, you can do that.
So we have a girl, so I got an internship. So I'm actually excited about that.
All right.
To transition into IT.
Or to transition into IT. Okay, that makes
Yeah.
sense because you're studying IT. So I was wondering why I'd been at that place, because you were you wouldn't be using IT and you wouldn't be applying what it is that you would have studied.
Yeah.
All right, but there's a question nonetheless that, all right, say nothing more. I wouldn't want you to, today's a Friday evening. How far is home? Don't tell me exactly where, but how far is home? Like about a half an hour drive or?
Being that I'll be taking public transport, maybe half an hour, because I'm just going to Crossroads.
So that's your final destination, Crossroads.
Yeah, yes, it is.
All right. I would want you to hurry up and get home because I don't want you to be on the road. And because this class is going to go up until late, I would prefer if you go. But I'm going to ask you to call me right now on WhatsApp. Let me ask you a question. And then you can hurry up and go. And then you join us as quickly as possible.
All right, no problem.
All right, cool. Take care.
Let me do that. All right.
I found the question, and I am just trying to type it so that I can project it for you. So give me half a second. I've not gone anywhere. Daniel, are you with us now? All right. Daniel, are you back with us? Nessa, you hearing me?
Yes, sir.
All right. Do me a favor, Nessa. Are you seeing the screen?
Yes, sir.
All right. You did very well last class. I'm going to ask you to keep up the same energy. Try that one for me, please, love.
So am I supposed to know this? I same thing? What was the last
Yes, man. On Newton Rapson, yeah, man.
one? That looks so different.
Same thing on Newton Rapson. Finish Nestor?
No, sir.
All right, but you're working though, right?
Yes.
Okay, cool. Daniel, are you back?
Oh, sir, I was always here.
No, you weren't.
Well, sir, I'm here.
Okay, yeah, because I've called you several times. All right, are you seeing the question projected?
Yes.
All right, have you started it?
Yes, sir.
All right, cool. Let me know when you guys finish. I'm right here. You guys finish the question now? Daniel, how far you reach? Nestor, how far you reach?
So,
Sir, I think I'll do it, sir.
You think you do it? Daniel, how far you reach?
finish.
Talk to me, I'm not understanding, I'm not hearing you, Daniel.
Sir,
I'm finished, so.
sir, what decimal place today?
Much what?
Decimal place.
I would say about 3. How many decimal places they put it to?
Yes, sir.
3?
So I put it to 4.
Okay, great. Daniel, how many decimal places they put it to?
To 4.
Okay, good. All right. Why are you laughing, Nestor?
No, sir. Nothing.
When you differentiate the function, what you got?
I got 2.6875.
When you differentiate the function, you get 2.787. When you differentiate the function, you say you get?
I repeat, 2.6875.
When you differentiate the function,
Yes.
when you differentiate,
Yes, sir. When I differentiate it, that's the denominator.
what are you talking about? Next, when you differentiate the function, what you got?
Sir, I mean differentiate, sir.
You're finding f dash of x.
Sir, for the second iteration?
Before you do before you do the second iteration, you have to differentiate the function. When you
Oh,
differentiate the function, what you get?
0.75?
Oh Lord, no. Look back at the examples they did last class, please. You have to get familiar with the terminology. See here? So when I'm asking you about differentiation, you know exactly what I'm talking about. So look back at that and then talk to me.
Um, um, So you mean like
Mhm.
4x cube?
Mm-hmm.
And that you mean, sir?
Yes, ma'am.
Okay.
4x cube what?
Sir, I never sure of that one there, but I put plus x.
Mm-mm. It's plus 1.
Sir, me know you know. So
So,
me
so
know me did calculate that separate. Come
go
never
and
can.
go finish that something for me properly, please. Come on, hurry up, man. Hurry up. It's just 2 of us here so far. Hurry up.
Sir, why you put plus 1?
The differential of x is 1. Because remember, x is raised to the first power. So the differential of x is 1. And the differential of the constant -1 is 0.
Okay.
Mm-hmm. All right. How we.
Sir, give me 1 second, sir.
All right, then cool.
Yeah, check it back. Yes, sir. I think I get the answer.
All right. Daniel, how you staying?
Sir, I'm all right.
All right. So I'm gonna, as I told you, I'm gonna see if I can do a new share. All right. So I did. The function is x to the fourth plus 1 minus 1. And the differential of the function is going to be 4x cubed plus 1. All agree with that one so far?
Yes, sir.
All right. So the first iteration uses in the 0.075. Do you agree with that? Huh?
Yes, sir. Yes, sir.
Good. So remember, it lies within the interval 0.5 and 1. So you then give it the interval to be 0.5 and 1. So we add the lower bound and the upper bound and divide it by 2. So 0.5 plus 1 is going to give you 1.5. Divide that by 2, you can get 0.75. Now, this is a formula. You have to remember the formula. You won't get the formula sheet in the exam. So you have to remember the formula. All right? Now, that formula will tell you what to do. So now, the second iteration is going to be given by that formula. And it's going to be 0.75 over so that's going to be the second iteration. All right. Now, recall that f of x is equals to recall that f of x is equals to x to the fourth plus 1 minus 1 and f dash of x is equals to 4 x cubed plus 1. So I'm going to find f of 0.75 look at that and tell me if that's correct. 0.75 to the fourth, not to the third, but to the fourth. So you should have 0.75 to the fourth plus 0.75 minus 1. So 0.75 to the fourth plus 0.75 minus 1. I get I get a positive value, 0.06641.
Yes, sir.
That you got?
Yes, sir.
All right, good job. Daniel, you're not talking to me tonight. What is it?
Yes, sir. I can barely hear you. Yeah, but I'm following.
All right, good job. All right, look at me if you agree with that. That's what I get for f dash of x, 2.6875. Let me know if you got it, yes or no.
Yes, sir. Yes, sir.
Daniel, that's what you got?
Yes, yes.
Okay, good.
Yes, sir.
So I'm now going to substitute this into my formula. And it's going to be 0.75. And it's f of x over this again 0.06641 over 2.6875. Let me see if I can do that quickly. 0.75 minus 0.06641 over 2.6875. That's what I got for my x2, 0.72529.
Yes, sir. Yes, sir. That.
Daniel?
Yeah, same answer.
Huh?
Yes, I got that.
Okay. And then now, my third iteration is going to be 0.72529. All right, so I'm going to have 0.72529 raised to the fourth power plus 0.725, 29 minus 1. 0.0002014. You got that? You got that? You got that, guys?
This one.
I never did the third iteration.
No, I don't finish the third
I'm
iteration.
close, but another. Okay.
I don't finish the third iteration, you know. 1, 2, 3, 0, 4. I don't finish the third iteration, you know. I'm just working out the values there. So 72529 72529 4 times 72529 to the fourth power. No, to the third power. No, plus 1.
Yeah.
All right. I'm getting 0.72444
9.
93. You got that?
Yes, sir. I run it off to 0.7245.
Yeah. So I'm coming now. So I said to how many decimal places a while ago? I said to 3 decimal places.
Yes,
So
sir.
the third iteration to 3 decimal places is 724. The third for the third iteration is 0.724. The fourth iteration is no, I
That
don't
the
do the
same,
fourth. The
that the
second
same thing like it for the fourth
no,
one.
but the second iteration is 0.725, and the third iteration is 0.724. So I have to go to a fourth iteration. You see what I'm saying? Look how I know when I stop. The third iteration is 0.724.
Oh,
I
yes,
set to
sir.
3 decimal places. So let me see if I can color code that.
Sir.
Yeah, it is tricky, but
Sir, if I run it off, you wanna get the 725?
no, to 3 decimal places. That's what I said for the question, right? Yeah, for 3 decimal places. I'm going to count the 3. I'm going to count 3 decimal places from the decimal point, and then look at the 4th digit. If the 4th digit is 5 or more, then I
Sir,
add 1 to the 3rd digit. So that the 4th digit there is 4. Go ahead.
So you only like round the 9 on the 4, make it 5, and then that. And I say round now.
No.
Okay.
So I go to the immediate one, not the one next to it. So I want 3 decimal places, I count 1,
Okay.
2, 3, and then I look at the 4th. If I wanted 4 decimal places, then it would be 7,
Okay.
2, 4, 5. And then
Yes,
up
sir.
here now. So up here to 3 decimal places is going to be 0.725. So we're off by 1,000 in value. So we have to have 4th iteration. Daniel, you see that? Daniel?
Yes. Yeah.
Did you get that?
Evening, sir.
Yeah,
Just
I
came
did.
in.
Yes, Anthony, how you do? Daniel, talk to me now, Papa.
Yeah, man, sir.
All right, good. All right, Utterly, we're on to our question. Utterly, you may want to take up the question. I'm going to send the document, but look at the question, Utterly, and can start working. They are going to be doing a 4th iteration for me. So, Utterly, see if you can start that for me, please.
So I did it already, you know.
Huh?
I did the 4th one already.
Oh, you did the 4th one already, Ernesto?
Yes, sir.
Okay, good. Daniel, did you do the 4th one?
No.
All right, I give you 2 minutes to do it. All right. All right, you hold on 1 minute, Nestor. Let Utterly start, try that one, and then Daniel finish off the 4th one.
Okay.
Sir, scroll back down to the 3rd iteration. Please.
I'm going to step away for 1 minute. That's where you want it to be?
Yeah, yes, sir.
I'm going to step away for 1 minute.
Can somebody send me the original question in the group, please? Anybody?
I am back.
Sir, I was asking for the original question, but I don't think anybody hear me because nobody responded. Okay.
Sit up there, honey. I
Thank
thought
you.
you got it. Hush.
No, man. It's all right.
So I think you can move on.
All right, was just waiting on you guys. Ouch.
We should do the fifth iteration.
No, it's not the fifth, it's the fourth.
Oh, okay.
So 0.724 493 9724 493 24 493. All right, so I hope you guys not tricking me in on anything that you're not understanding. If I'm getting the answer, that you're not really getting the answer.
Yes, sir.
Nice. Because if not, I need to know what I need to do to get you up to where you're supposed to be. Otto, where you stay?
I'm working it, sir.
Good job, my love. 0.00264 6248. 2624. 0.002624. 2624. And then this is going to be 72493. 72493. 5112. 521111. 1117. What is that again? 521111. 3 ones. 72493. And this is going to be 2.5 21117. 3 ones and a 7. Yes. And 26, 24. And that is going to be 0.724 493 minus 0.002624 over 2.5211117. Okay, and then I'm going to get 0.7 2 3 4 5 2 723 452 and 2. Stockstone. That not help me. Wow. You see what is happening here? That's not helping me at all. Let me ask you. Look at that answer. Do I need to do another iteration?
Sir, I not get that answer. Sir, I get the same thing as the third iteration.
Oh, well. Daniel, what you got?
So I got something different.
Can you double check for me, please?
Yes, sir.
So what I'm seeing different is that I have for the first function, the first five decimal places are zeros.
The first 5 decimal places are zeros for this piece up here?
Yes, sir.
The first 5 decimal places, hold on there. Let me see if I did something.
Yeah, let me check again, actually.
Oh, yeah, man, you're right. You're right. You're correct, man. You're correct. I didn't recognize. You're right, Daniel. You are correct. Let me turn up this light. Let me turn up my light. You're correct, Papa.
Oh, okay. So
You're correct. It's why it's important for you to talk to me in class. 1, 2, 3, 4, 5, 3, 2, 3, 4, and it's not the 1, 2, 3, 4, 5, 6, 2. Yeah, my bad. Wow, how could I do this? You got the 2.5 to 111, Daniel?
yes. Yes, sir.
2, 3, 4, 5. You're correct. I didn't recognize it was to the 6th power. You're correct. Let me see, how did I do this now? Three, 2, 3, 4, 5. And then I now end up with 7, 2, 4, 4, 9, 1, 4, 9, 2. Can I stop now?
Yes, sir.
Yeah, man. Yep. Very good, guys. Otto, I'm going to give you a couple minutes because I want to hear your headspace.
Okay, so that's done the second iteration, going on to the next one. Just give me a second.
All right, no problem. And the rest of you, I want you to look back at what it is that you're doing. Just look back at it and just go through. Yes, you got the answer, but see if you can put it back now to long-term memory, because I want to move into something new now. Just even out a little time to finish up the stuff. So I'm gonna give you about 5 minutes auto, and then we start back, all right?
Okay, no problem.
All right. How are we now? Where are we?
Finish.
Okay, and you got the same answer as we did.
Yes, sir.
Good job.
Mhm.
So I am here sitting and reflecting, and I'm going to help you guys how to prepare for exam. It doesn't have to necessarily be math, but the exams on a whole. I'm finished with Newton Ramsden. Done. I will come to class and do one question here and there, but I'm finished with the topic. What is going to be important for you guys is to go through the topic on your own. Every now and again, you just go through and look at the areas we have previously covered. When you do this, it keeps the topics fresh in your heads until you can master it. That means if 2 weeks from now, we call you and answer to something, you know exactly what to do. But if you understand it now and then put it up for exam time, you are going to forget it. You have to bring it to long-term memory by practicing and practicing and practicing and more practicing. Very important. Do we have an agreement?
Yes, sir.
All right.
Ah,
Yes, my love. You answer the question, Otto?
no, I'm saying yes, I get it.
Oh,
The
okay, got
practice
you.
thing, yeah.
Got you. All right, so I'm finished with Newton Ramsden, and making an effort now to start McLaren's expansion. I'm making an effort to start McLaren's expansion, but before I do, I need to do a quick revision with you. Before I do, I need to do a quick revision. Are you seeing the screen?
Yes, sir.
Mm-hmm. Need to do a quick revision on differentiation. That's so because earlier I asked a question and I wasn't so convinced that you really remembered how to differentiate. And the areas that we're looking at now are areas under applications to differentiation. So it comes with the premise that you already know how to differentiate. Comes with the premise that you already know how to differentiate. Fair enough?
Yes, sir.
Mm-hmm. When I'm differentiating the exponential function, the differential of the exponential function is the function itself. So let us look at example 1. The differentiation of the exponential function is the exponential function itself. Example 1, y is equal to e to the x. The differential of e to the x is e to the x. The differential of e to the x is e to the x. So I'm going to end up putting 1 e to the x. The differential of the exponential function is the function itself. Let us look at number 2. Y is equals to e to the 2x. The differential of the exponential function is the exponential function itself. So I'm going to have y equals, sorry, dy by dx is also going to be equals to e to the 2x. But I have to differentiate. I have to differentiate the 2x. And the differential of the 2x is going to give me 2. It's going to give me 2. It's going to give me 2. So what is going to happen is I'm going to have 2 e to the 2x. 2 e to the 2x. So the differential of the exponential function is the exponential function itself. So when I differentiate it, I'm going to end up with the exponential function, which is 2, which is e to the x squared, or e to the 2x, I'm sorry. But when I differentiate the exponential function, which is 2x, I'm going to get 2. So it's going to become 2 e to the 2x. Am I clear right there?
Yes, sir.
If I'm not clear, tell me no. All right, look, do me a favor. Look at 3, 4, 5 bias on your own for me now, and then I'll come back to you. 3, 4, 5 on your own. When I say come back to you, I'm not going anywhere now, but I want you to just try that on your own. 3, 4, 5 on your own for me, and then I'll come back to with the question. Wherever you're having a difficulty, always please feel free to say to me, sir. Now follow. Never, ever, ever get afraid to let me know what is happening to you and how you're feeling. Feel comfortable with that now, guys?
Yes, sir.
So just remember now, the differential of the exponential function is the exponential function itself. The differential of the exponential function is the exponential function itself. And then you're going to differentiate the function and put that in the front of it. So let me start with 5 and work my way back up to number 3. 5 says y equals e to the 3x squared plus 5x minus 7. The differential of that exponential function will be the exponential function itself. So you will recognize that I'm going to still end up with e to the 3x squared plus 5x minus 7 in my answer, which is at the end of the function, which is right here.
I differentiate everything except the constant.
And then I'm going to differentiate everything, right? And then no, the differential of 3x squared is going to be 6x, and the differential of 5x is going to be 5. Remember, the differential of the constant is 0.
Constant is, yeah.
Right. So I'm going to end up with now 6x plus 5 times the exponential function itself. Understood?
Yes, sir.
Good job. Is Shane back with us now?
Yes, I am, sir.
Okay, good.
But question, sir, when we were doing differentiation before, we never deduct like 1 or something like that.
Yeah.
But none of that now going necessary.
Same, it go along same way. Yeah, man, it go along same way. Watch it. So we have 3x squared. When we differentiate in 3x squared, this 2 is going to be multiplied by this 3 to give me this 6.
Yeah.
And then we have x squared, and I reduce the power by 1. So instead of x squared, it's going to be x to the first, which is right here. So.
Oh, so it just go over there, so and then okay.
Yeah. So when I differentiate 3x squared plus 5x plus 7, that's what I end up having. The differential of 3x squared now becomes 6x, and the differential of 5x becomes just 5.
Just 5.
So it's right. So we're subtracting 1 from the power. Same way, man. Same thing. Now change that.
Okay. Yeah, I see it, sir. But then you multiply it back by the
right. Good. And
it.
that's how you differentiate the exponential functions. Remember, you have many different types of differentiation, many different scenarios for the differentiation. The fundamental principle, which is what you just alluded to, that you are going to be reducing the power by 1, still stands. That not change.
Okay.
That not change. But what will change is you'll get differentiation of a product, you'll get a differentiation of a quotient, you'll get a differentiation of a chain, you'll get the differentiation of the power rule, you'll get the differentiation of the exponential function. You may also get the differential of a logarithmic function, right? But and in each of those, you will have different rules inside of them, right? So think of you working in an organization, and the organization has rules, but you go to a particular unit, and in that particular unit within the organization, you find other rules in there. Anybody know what they're talking about?
Yeah.
Yeah, man. Yeah. So for example, at some point in time, I used to work in the financial system sector. And if you're on the front line, say, for example, you're cashing, you can't be eating on the front line because the customers are there in front of you. That's a no-no. But if you're at the back end, while you're working, you can't even drop a 2 biscuit in your mouth or 3 biscuit. Talk truth.
Yes, sir.
Yeah, man. So it's a different situation. Especially if you're in an office space by yourself, you may be able to drink a smoothie while you're working, even if you're on an online meeting. But once a customer comes in, now you can push that sitting to the side, and you behave nicely and so forth. And when the customer gone, you start slurping you something again. So there are rules within so the organization may say to you, you cannot eat on the job. Eating is only restricted in the cafeteria or the lunchroom, wherever no one call it. But we find out that people in their individual office spaces, may come down. The top boss may decide that, today I'm going to eat with my staff and come down and You know, when top boss bust the lunchroom door, everybody stop talk in the quiet. Right? So boss man, steer the plan, take my lunch upstairs, someone please. So you have rules within the zone. So the point I'm making is the basic rule stands. When I'm differentiating, I'm subtracting one from the power. All right? But you have rules within the rules within the rules. Quotient rule, product rule, chain rule, power rule, exponential rule, logarithmic rule. All right? So when you look at for argument's sake, e to the x squared, when you differentiate the exponential function, you get by the exponential function itself. So in the question, in your answer, you must have at the same exponential function, e to the x squared. But I must now differentiate the x squared, the function. And when I differentiate x squared, I'm going to get 2x. So that's why I have the 2x in front. So my final answer is going to be 2x e to the x squared. You have to remember those rules. So why are you emphasizing it? Thanks for asking. I'm so emphasizing that point because when you go into the exam, you may get a Maclaurin's expansion. The topic that I'm going to be moving on to next, you may get a Maclaurin's expansion with an exponential function embedded. So because it's a question on applications of differentiation, like the one we just did, you recognize I had to differentiate in Newton-Raphson? Hello, somebody?
Yes, sir. Yes, sir.
Good. So if your differentiation was off, I guarantee you, when you did the first iteration, and then move on to the second iteration would have gone so far off from the first iteration. And the third iteration would have gone about it these days. One will go east, one will go west. So why is this so? Because your differentiation was off. Your differentiation was off. So if your differentiation is off, best believe that your answers will not converge to the same thing. Your answers will not converge. Case in point, you see what I did? What I did was to put 2 zeros in front of the 6 because I really and truly did not look at the end of the function to see that it was raised to the -6. The exponential function was raised to -6. I only assumed that it raised to the -3 because all the other questions that I did, it was raised to -3. It was raised to the -3rd power. So I only assumed, not until Daniel says, sir, I got 5 zeros in front. I said, oopsie daisy, let me check. And for sure, it was to the 6th power. So he's correct that he would have gotten 5 digits there. And you recognize what sir said to you? Sir said to you, ask the question, do you have to do a 4th iteration? And I said, yes, because to 3 decimal places, your answer was not coming out to be exact. But sir, one was just 1,000th of a unit out. It doesn't matter. It makes a big difference. It makes a big difference. Do you know if you, say, for example, drop 1 drop of radioactive substance in one of our catchment area, what chances are the whole of in Jamaica dead? It is that infectious. Same difference here. 1 digit is out and it throws out everything. Throws out everything. So I'm saying to you, just be careful, please. Be careful with what it is that you're doing. Be careful with how it is that you're doing the calculation. All right? Any questions?
No, sir.
All right, so let me remind you now of the differentiation that we just did. We just look at the exponential function. Y is equal to e to the x squared plus 5. Sir, you said to us that when we differentiate the exponential function, you're going to end up getting at the exponential function itself, and then the difference times the differentiation of the power. See here? E to the x squared over x plus 5. See to yourself? E to the x squared over x plus 5. Oh, but sir, this in red is the final answer. Yeah, it is the final answer. So it's going to be the final answer, and it contains the same thing as the original question. No, there's something else that needs to come with it. What needs to come with it is going to be now the differential of the x squared over x plus 5. The x squared over x plus 5 is now going to come in front, and this is going to be the differential. Allow me to walk you through as a refresher of this differentiation, because I did it, but we did it in Calculus 1. This, what I'm doing here, is a review. It's not to reteach, it's to review it. Does anyone know what rule this entails? What is this rule? We're gonna have something
Quotient rules.
the quotient rule, right? And do you remember, Daniel, how to differentiate the quotient?
No, sir.
The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator square. The denominator, does that ring a bell to anybody?
So it's coming back, but I have to go and practice this. But it'll come back, I just saying it. I remember you saying.
All right, good. That's all I want to know. Whether or not to remember it, but just remember at least it jogs your memory that your mom, we hear one song with so and so. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator square. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Very, very, very important that you remember that. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator square. And if you remember that, you are good to go. Mm-hmm. All right. Let me close you. Why is this not working? I'm trying to put something as a recall for you, but that's a text flow. What? Undo. Okay, I don't know what happened a while ago. But here's the rule. The denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Watch me now. Don't write. Watch me. Spotlight so you can see what I'm talking about. I'm talking about the x squared over x plus 5. That's what I'm interested in. The x squared over the x plus 5. Not interested in anything else, just the x squared over the x plus 5. So it's a denominator. I'm going to put x plus 5. See it here, so? That's the denominator, x plus 5. I write it back. Times the differentiation of the numerator. When I'm differentiating the numerator, x squared becomes 2x. So I'm multiplying that by that. So it's a denominator, see here, x plus 5, I write it back. So every time you call it something, you write them back, yeah. So it's a denominator, write it back, times, see here, in parentheses, the differentiation of the numerator, good. When I differentiate x squared, I'm going to get 2x, good. Minus the numerator, every time I call the term, I put it back. It's minus the numerator, it's going to be minus x squared, times the differentiation of the denominator. I'm going to differentiate x plus 5, but hold on, sir. The differential of a constant is equal to 0. That means when I differentiate positive 5, I'm going to get 0 or 2. But when you differentiate x, what do you get? Question. When you differentiate x, what do you get?
1.
1. So that's why I have this 1 right here in parentheses. And then now it is all over the denominator squared. It is all over the denominator squared. So this is x plus 5 is going to be x plus 5 all squared. Differentiation ends right here. What is really left is going to be little school mathematics. Little school mathematics. And little school mathematics is where you do the little easy algebra then. Right? And it comes into play. Makes a big difference. Right, watch me now. I have all right, watch me now. So I'm going to be removing the parentheses. So this is going to be x times 2x is 2x squared. And then I don't have anything else to multiply the x by. So I'm going to multiply the 5 by the 2x. And 5 times 2x is going to be 10x. So this is a 10x. Minus x squared times 1 is a simple minus x squared. And then I put in like terms together. There are only 2 terms here that are similar. The 2x squared and the negative x squared. I'm going to add the pair of them together. 2x squared minus x squared is just going to give me 1x squared. So see it here, so I have the 1x squared. And because the positive 10x is a standalone item, I'm going to write back the positive 10x right there as a standalone. And then I could leave this as my answer. But I recognize that there's something else that can be done. What can be done, sir? I looked in the numerator and I recognize that something in the numerator can factor out. Then, sir, we have to do it, yeah, man. You always write your answer in its simplest form. Always write your answer in its simplest form. So to simplify that answer, I'm going to just factor out to give me x times x plus 10 over x plus 5 to the 6, x plus 5 to the second power, I'm sorry. And then the question is asked, sir, what if I don't factor it out? Will I be wrong? Technically, no. But presentation-wise, it now looks up cute. Any questions so far?
No, sir.
Not yet.
Not yet. I like the sound of that one. Not yet. All right. So we did an example on the product on the quotient rule. We need to do an example on the product rule. All right. So what I want you to do is to try and jog your memory. I'm trying to get this thing. All right. I want you to try and jog your memory. Through this question. It's another question like this one with the exponential function. Go through it, see if you understand it. I'm right here. I'm going to give you, what time is it now? Whoa, time is running, 7:41. I'm giving you 5 minutes to look through this question as a recap. This is a recap, you know. And then now, whatever questions you have, just jot them down. Jot down the questions. And it's a good thing when you jot the questions down so that when you're revising, you can remember the questions that you're asking. Jot the question down so we can have a conversation with it. All right, start for me, please. 5 minutes. You have 4.5 minutes left.
Mr. Shan? Sir?
Sorry, I couldn't get to unmute. Sorry about that. Yes, Shani. Shani?
I was just wondering where you were.
Oh, you man, I'm right there. So,
You're
do you
here.
understand? Do you understand who I got that? All of you?
Yes, sir.
Feels a little
Yeah.
comfortable. Coming back to you. We've done this before, in calculus one, And remember, because time is short, I really can't go through, what it is that I've already done. But if you have a difficulty, I would definitely be more than happy to just go through to refresh your memory. All right, so that's a product rule. The first times the differentiation of the second plus the second times the differentiation of the first. And this is a product because I'm multiplying one term. Sorry, I'm differentiating two terms, one term, but it is a product. Look back at this one in 1 minute. Look back at this one. The first times the differentiation of the second plus the second times the differentiation of the first. The first times the differentiation plus the second times the differentiation of the first. Look at that for me, please. Mhm. How is it? How it feel?
I have answer. I'm not trying to remember everything.
Mm-hmm. Let me go through this one with you. So it's the first times the differentiation of the second plus the second times the differentiation of the first. The first is 3x, I write it back, times the differentiation of the second, that's an exponential function. Oh, sir, so it again. The differentiation of the exponential function is the exponential function itself. So that's why I write it back, e to the x squared plus e to the x plus 1. The differentiation of the exponential function is the exponential function itself. So because of that, I'm writing it back. Times the function. What's a function? X plus 1. When I differentiate x plus 1, I'm going to get just 1. Because the differentiation of the plus 1 is 0. And the differentiation of x is 1. So that's how we got that 1. That's how we got that 1. Plus the second, I write it back, e to the x plus 1 times now the differentiation of the first. When I differentiate the first, it's going to be 2 times 3, 6. I'm going to have 6x. Boom. So what this works out to be now is that this times this gives me this. This 1 times 3x squared times x e to the x plus 1 is simply this. And 6x times e to the x plus 1 is 6x e to the x plus 1. You'll always be able to factorize the exponent, the exponential form. You'll always be able to factorize the exponential form based on the nature of how the question is done. So I'm going to say to myself, what is common here and is common there? And I recognize that the e to the x plus 1 are common, so I factor it out. But in the 3x squared,
3x and 6x.
very good, and the 6x, I recognize that 3x is common because 3x can go into 3x squared and it can also go into 6x. So I took the 3x.
3x.
And then what is going to be left now is going to be what I multiply by 3x to give me 3x squared is simply x. I want to multiply by 3x to give me 6x is going to be simply 2. And then this is not my answer. I'm just rearranging it, put the exponential form at the end of it to get that stuff there. So, yes, we have done these before. It's a mere refresher that we're looking at. Refresher because we have to know go ahead with our differentiation of the different forms. So we look at the exponential function, look at the product rule, quotient rule, and I'm not doing the chain rule because the chain rule is simple. All right, so tell me that you understand that, please, guys. Let me just do this piece quickly before I move into my Clarence. I have to do, every time we meet, I have to start and finish a topic because it's really a short semester, shortened version. And let me just point out something. The class is undersubscribed. You may have 1 or 2 more joining on for next week. I will send them the recording so that they can see what is happening for the last 2 classes. By then, the class is undersubscribed, meaning the institution says if it is not 15 and above, we can't run the course. But I remember having a conversation with Ottilie from last semester. And she said, sir, I need to make a decision. Are you sure that this is going to happen? And, based on the trajectory, I said to her, yes. So at this point in time, I couldn't go back to her to say, why it never happened and so forth and so on. So I'm expected to have to give some levels of justification and that, So I say this to say to you, we are small in numbers. I'm going to lobby on your behalf. I'm going to speak to them and say, no, sir, I've taken the decision to just run this because there are some students who are finalizing and need this math course out of the way. Please, don't make me feel shame. Already I'm going to be begging, I want to be able to say, see there, look how well they performed. We are small in numbers, capitalize on it. You can ask the questions in a smaller setting, capitalize on it. Do I have your promise?
Yes, sir.
All right, thank you.
Yes, sir.
Yes, ma'am. All right. Let me look at the natural logarithm. The natural logarithm function is denoted lnx, right? So the differential of the logarithmic function is 1 over the function. So I'm telling you, differentiation is differentiation, but you have different rules in differentiation. So when I'm differentiating the logarithmic function, it's going to be 1 over the function times the differential of the function itself, right? So you notice when I did the exponential function just now, the exponential function is, when I differentiate the exponential function, I get back the exponential function itself. But I have to know times it by the differential of the power function. This one here, the natural logarithm, the differential of the natural logarithm is going to be 1 over the function times the differential of the function itself. So for example, if I gave you y equals ln x, the differential of y equals ln x is going to be 1 over x. Why, sir? Because the natural logarithm function, I'm going to put 1 over the function. What is a function? Everything outside of the ln. The ln there is just telling us to put 1 over it. The ln is telling me to put 1 over it. All right? And then I'm going to times it by the differential of x. When I differentiate x, I'm going to get 1. And I differentiate this x, I'm going to get 1. So that's why it's going to be 1 times 1 is 1 over x. Let us look at y equals ln x squared. When I differentiate this function and put it, once I get a logarithmic function, so how do you know the logarithmic function? It is 1 over x. So once I differentiate the logarithmic function, I'm going to get once I differentiate the logarithmic function, I'm going to get 1 over that function. I'm going to get 1 over that function. So the differential of 1 of ln x squared is going to be 1 over x squared times the differential of x squared. And the differential of x squared is going to be 2x. Agreed? So I'm going to have 2x over x squared. And then I can cancel out some stuff. Let me show you what it is. See here, the differential of ln x squared is going to be 1 over x squared times the differential of x squared. When I differentiate x squared, I'm going to get 2x. So this number becomes 2x over x squared. See here, 2x over x squared. I can cancel one of the x's, so it's going to give me 2 over x. I want you to look at it for another minute, and I want you to tell me whether or not you understand that. The natural logarithm function, when I get something like that, it's going to be the differential of that is going to be 1 over x times the differential of a function.
Sir, why is that 1 over x again?
Ask again.
It's always going to be 1 over x.
Yes.
Okay.
1 over the function. So if it is ln x squared, it's not going to be 1 over x. It's going to be 1 over x squared. So whatever the function is, it's going to be 1 over that function.
Okay. Okay.
Yeah. So let us look at another example. ln x plus 1. ln x plus 1. And so many of us could have other terms in it. Yeah, man. So ln x plus 1 is going to be 1 over x plus 1. 1 over x plus 1. 1 over x plus 1. And then I'm going to times it by the differential of x plus 1, which is 1. See here, that 1. So I'm going to be left with 1 over x plus 1. So it carries forward for that one as well. So look at that. 1 over x plus 1 times the differential of what is in a function. When I differentiate plus 1, I'm going to get 0. When I differentiate x, I get 1. So I'm going to multiply that 1 by the 1 over x plus 1, and I get this. Use this example to work this one for me, please. I'll give you 2 minutes. Let me know when you're done, please. Oh, somebody is joining. Finish working on that, guys?
Sir, move them up. Oh, it's just 3, okay.
I was just about to say, well, go on.
Would it be 6 over the answer? 6 over that?
Bob.
Yes, right. Next.
Very nice. I love it. Guys, I'm depending on you to do it. Very nice. Very, very, very nice. Very nice. Nice. Nice job. Very nice. All right. I will send those to you. Everybody has got that? The differential of the ln function, the natural logarithmic function is going to be 1 over the function. So it's going to be 1 over 2x plus 1 to the third power. So that's the first part. But now I have to differentiate 2x plus 1 raised to the third power. That's the power rule. So watch what is going to happen. This 3 is going to come in front of here. It is that. Then Shani, see it here, is going to be 2x plus 1 to the second power because I'm reducing it by 1. I'm reducing it by 1. And then I have to multiply by the differential on the inside, which is going to be 2. So this 2 times this 3 gives me the 6. And I'm going to have 2x plus 1 to the second power. And remember, in my 2x plus 1 to the third, I'm going to have 3 of them. So I cancel out 2 of them, leaving this 1. All right, I'm going to send this off to you tonight so that at least you can look back at it in your own review. But guess what? It's 8:30. We need to wrap it up. So allow me to just go through a thing or two in the Maclaren's. So for the Maclaren's theorem of approximation, we're going to be looking at functions of infinite series. Then a function, when I talk about infinite series, it means it can go long, it have no end, infinite, right? So when you get a function, a question like that, it may say to you up to and including a particular term. But sometimes when you get the function, the term in itself terminates, right? So what this is saying is that f dash of 0, this is going to be f of x is going to be equal to f of 0. It means that I'm going to put 0 into the function and work out that value. That's going to be the first term. Then plus f dash of 0 means that I'm going to find the first differential, substitute 0 in the first differential, and then times it by x. And then I'm going to have f double dash of 0. F double dash of 0, double dash is the second differential. I'm going to find the second differential, substitute 0 into it, and divide it by 2 factorial times x squared. Plus, find the third differential. When I get the third differential, I'm going to substitute 0 in there, get that answer, and then divide it by 3 factorial times x cubed. So if you notice, this 2 corresponds with this 2, this 3 corresponds with this 3. Then, sir, oh, you don't have the 1 over here. Yeah, man, I can have it. So this is why I write it here. So this 1 corresponds to this 1, and then this 0 corresponds to x to the 0. What do you know about my x to the 0 here, sir? Yeah, because anything raised to the power 0 is, somebody say 1.
1.
Right. So it's like I have 1 here, and 1 is known as a multiplicative identity. So if I multiply anything by 1, it's still 1 as the answer. All right. So as a quick exercise, factorial notation, n factorial is n factorial times n minus 1 factorial times n minus 2 factorial times n minus 3 factorial, all the way down until I reach a term I'm going to call k. So what do you mean by that? Let us check. 5 factorial is going to be 5 factorial, then 5 minus 1 times 4 factorial, then 4 minus, then 5 minus 2 times 3 factorial, then 5 minus 3 times 2 factorial, then 5 minus 4 times 1 factorial times itself. times a 1. So 5 factorial is going to be 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? So once I'm doing the factorial, that's what it is that I'm going to be doing. 15 factorial is 15 times 14 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I guess you get the gist of it. All right. Now I don't expect you to be using a factorial to do the multiplication out like this. I would expect you to find a function, the factorial function on a calculator. And the factorial function is denoted exclamation sign. Exclamation sign. So look at your calculator now and see if your exclamation sign is there.
Sir, we're X.
X to the minus 1.
Yes, sir.
Yeah.
Fine.
So note, the factorial notation is denoted by the exclamation sign, right? And it is often found over the X to the minus sign button. X to the minus 1 button. Can everybody identify that on their calculator?
Yes, sir. I said I found it. Yeah.
Yeah, good.
Yes, sir. I found mine.
Nice. So put in 5 and then press the exclamation and see if you get 120.
Yes, sir.
Good job. And okay, so that's it for that one. Okay. All right, let's just look at an example. This example here, and I think this needs to go up to the end of the class. This example here is an example on Maclaren's theorem. So I want to use Maclaurin's theorem to expand 1 over x plus 1 up to and including the term in x to the 5th power. I want you to use Maclaurin's theorem to expand 1 over x plus 1 up to and including the term in x to the 5th. That means again, I want the term in x to the 1st, x to the 2nd, x to the 3rd, x to the 4th, and I'm going to include the term x to the 5th. So you're going to end up doing the differentiation 5 times. You're finding f dash of x, f double dash, f triple dash, f to the 4th, f to the 5th. Can you see why I had to spend some time a while ago to refresh differentiation with you? Yes or no?
Yes, sir.
Because you're going to go through all of that differentiation now. So let us look at the solution. So I'm going to let f of x be equal to the function. They didn't name the function for me, so I'm going to name the function. So it's very important to name the function. Make sure say if utterly I walk on road and somebody say, I am sexy girl. Utterly I go say, what we might talk to? Boy, bright. Utterly now go look back. And if Shane see somebody and say, I am sweet biscuit. And I mean my talk, I'm on a biscuit. Right? So if, for example, no, Nesta is walking and the person say, excuse me, miss, she will stop. And I expect all of you females to stop. Why? Because it may be a stranger and they don't know your name, but they gave you the correct title. Browning. No, sir. You can't look on a girl and call that Browning. Browning, come here to me. No, man. So just as how we don't respond. By the way, let me ask a question to the females in the class. If somebody, you're walking on the road and somebody say, yo, Browning, look here. Would you be engaging that person in a conversation? Question.
Sir, not me.
Okay, good.
Depends
So
on the also.
say it again.
I guess it depends on the tone. Because I'm short, some people would say, shorty, sometimes some people don't remember.
Well, I mean, because you know that you're not so tall that, you may want to, yeah, I see your point. But the truth of the matter is, some women, for a fact, they don't even, in matter of fact, I heard of situations where one lecturer who has a doctorate, and somebody says, let's say, Miss Smith, and a person turned around and said, I am not Miss Smith, I am Dr. Smith. I'm Mr. Cooper on you too. That was my response when I heard it. Mr. Cooper on you too. But the truth of the matter is, Miss Smith has earned her doctorate. So guess what? You see, because she earned her doctorate, you have to give her the title. And by extension, and somebody may say, but sorry, not upon your birth certificate, but I don't care. Put it this way. When you guys earn your bachelor's in MIS or IT, the man have to give some respect. Because you know, can't money in the workplace now. So the man can't pay you the same amount of money like he was paying you before you have a degree. The man have to put on a title upon your name, right? So if I'm going to put on a $2,000 upon his salary, I don't care how much, but he might have to put on something because you have now earned your stuff. Now, mark you. I was having a conversation with a student, and the student said to me, I said, oh, so like when you have a degree from the college, you got an increase in your salary? And the student said to me, well, sir, there's no increase, because the truth is the job that I'm in really requires a degree. But because I was going to school, they hired me without a degree. I said, okay, fine. I tell them thank you. But now that you finish a degree, they have to go find something and get a promotion in the business place. Because you have to put on a title upon your name. Commit something, right? So you have to know your worth. Same thing with that topic here. The man them say 1 over x plus 1, they have to get one title. Call him f of x for argument's sake, since the formula is f of x and f of x and f of x and f of this and f of that. Then so we can't call it y. Yeah, but we call it y, you may confuse yourself when you're substituting it into the function. So just call it what it is. All right? So let's go. So very important to name the function. So remember the first part of this thing says we're going to substitute 0, and incidentally, when you every time at every point you differentiate the function, you're going to substitute 0 in the function, right? That's why we have these f double dash 0, f triple dash 0, f to the 4th dash 0, all the way down to f to the n 0. And the first term we also need to find the 0 of that. So look at what I'm doing. F of x is equal to this. Let me just copy and fix up this a little. Oh no, Oh yeah, I'm correct. I'll show you something. What it is that I'm doing here. So you can actually see. So I'm finding f of 0. I'm finding f of 0. I'm finding f of 0. So anywhere in the function I see x, I put 0. So f of 0, see it right here, so is going to be 1 over 0 plus 1, 0 plus 1. 0 plus 1 is 1. So I'm going to have 1 over 1. 1 over 1 is going to be 1. So that's why f of 0 here is 1. It's very important for you to evaluate this function. And this is a part. So guess what? If your differentiation is off, your f of your 0 of the differentials are going to be off. And a question like this, remember I confessed to you last week, that I'm doing different things differently for this course. It's a fast track. So what I'm doing, I'm teaching the big boys and get them out of the way from early. So like how we've completed the Newton-Raphson. Newton-Raphson come for enough marks. Newton-Raphson last time it came for 11 marks. So if you can go out in a paper, in an exam and do the Newton-Raphson and get a full 11 marks, 11 marks out of 20 or 55% that. So make sure that you understand the stuff, and you made a promise to me today that you're going to do what it is that you need to do. All right. So let's move on now. Are you understanding this piece here?
Yes, sir.
Yeah, man. Then for the first derivative, it means that I need to differentiate this. Watch me. Oh, sir, now I see why you had to refresh your memories with the different rules of differentiation. Because the topic we are doing is called application to differentiation. No, I see, sir, because now we are going to be forced to do the differentiations. And if you all agree, I say yes. That's why I did what I did just now. So this is what is going to happen. This is what is going to happen. It's a denominator. See here, I call it, I write it back. Times the differentiation of the numerator. When I differentiate 1, I get 0. See here, so minus the numerator, minus 1. See here, so times the differentiation of the denominator. When I differentiate the denominator here, I'm going to get 1. See here, times 1. All over the denominator square. X plus 1, all square. See here, so boom. Differentiation ends right here. Take a minute and look at this and see if you can agree with me that this is a differentiation.
Yes, sir.
Very good. What about the others though?
Sir, the bottom, okay, get it on the side.
Always the denominator square.
Denominator square, yeah.
Every single time. Any other question? All right. So I'm going to fix up this a little bit. I'm going to fix it up a little bit. What do you mean by fix up, sir? I want something to the 0 right here, so when I multiply this, I'm going to get 0. But when I multiply -1 by -1, I'm going to get -1. When I multiply -1 by 1, sorry, I'm going to get -1. See it up yourself? Boom. Over the x plus 1 all squared, see here? Boom. So what I'm going to do now is to find the zeros of this. So I'm putting 0 in there. So f dash of 0 is going to be this over 0 plus 1 all squared. 0 plus 1 is 1, and 1 squared is 1. So I'm going to have -1 over 1. which is simply -1. Tell me if you see that and agree with that. Talk to me now. Hello, somebody?
I see it's here.
All right, cool. All right. And then now we have to differentiate the first differential in order to obtain the second differential. So they have to integrate, I mean, not integrate. They have to differentiate the first one and then differentiate the first one, the first one to get the second one, differentiate the second one to get the third one. So remember now, x plus 1 is a power rule. And when I'm doing the power rule, it's going to be see here, x plus 1 all square, x plus 1 all square. It's going to be this 2 is going to come in front of here, see it right here, so. And then I'm going to reduce it by 1. So I'm going to write by the x plus 1, see it right here, so. And I reduce it by 1, so it's 2 minus 1, see it right here, so. And then now times the differential of the inside here, so. And I differentiate positive 1, I get 0. And I differentiate x, I can get 1, see it right here, so. Boom. So this 2 is this 2. And this x plus 1 to the 2 minus 1 is the same thing as x plus 1 to the first power times 1. And 1 times 2 is 2 times x plus 1. Remember, anything raised to the power 1 is the same thing. Look at that and tell me if you see and understand that power rule.
Yes, sir. Just to remember how to do the power rule, all different rules. That's just it. Because once you remember it, then you're good.
Mm-hmm. So it means then I have a little bit of work to do so that we can put it to long-term memory. A little bit of work to do so we can put it to long-term memory. So I'm going to now have all of this with this. So this is going to become now -1 over all of that. See here? Oopsie daisy. So my second derivative is going to be, right, no, that's not true. So I'm just showing you how to do the power rule. So look at what is going to happen now. I am going to find a second derivative. So remember the first one was this. This is the first derivative that I'm recalling here. See it right here, so I'm going to differentiate the first one in order to get the second one. So look at what I'm doing. It's the denominator, x plus 1 squared, see it here, so, times the differentiation of the numerator, see it here, so, minus the numerator, so it's minus a -1, see it here, so, times the differentiation of the denominator. But remember, we know how to differentiate the denominator now, right? So it's going to be this 2 in front, see it here, x plus 1 and reduce it by 1. I don't have to put that 1 there because it's a 1. And then times the differential of the inside, which is this one. And then now I'm going to square this. So it's going to become x plus 1 square. That gives me to the 4th power. And then when I work it out, all of this goes to 0 because 0 times anything is 0. And -1 times -1 gives me a +1. And +1 times 2 is 2. And 2 times 1 is 2. And then now this x plus 1 cancels with one of that. So I'm going to have 2 over x plus 1 to the 3rd power. I want you to do me a favor. I said a lot of things here. I couldn't write everything here because I don't have enough space based on how I put it here. What I want you to do for me, I want you to understand this one question. So even if I do one question with you tonight, at least you're leaving the class with a full understanding. I want you to differentiate this function f dash of x for me and tell me if after you differentiate it, you're getting my f double dash of x like I did right here. I have piece of the differentiation here. So go ahead and do the simplification for me, please, quick and fast, and let me know what is happening. Hello, somebody? Talk to me, man.
So what's understand where it's supposed to work? What do you want us to do?
I just wanted you to confirm the differential of this f dash of x to f double dash of x. But I was saying to you that I have a piece of it right here. It don't make sense to even go through the rest of the question if you're not following the differentiation on your own. So
Yeah,
that's why I want you to do it. So that's why I stop.
So 4 to the third. Okay. 2.
All right, sir, I have a question.
Go right ahead.
On the point where you're going to substitute 0 in the function for x, isn't the denominator going to,
Remember, you have a 1 here, now,
Oh,
so it's not going to go to 0. That's what you're going to ask me, if it's not going to go to 0.
all right.
Yeah, no. It is. There's a 1 right there. So 0 plus 1 is 1, and 1 squared is 1. Because remember also, Daniel, that we can't divide by a 0. It doesn't exist in mathematics. It's undefined. I'm waiting to hear from you guys. Hello, somebody.
Sir, it makes sense to me, sir. I got it.
Very nice.
Oh,
All right.
what I'm drawing a blank on though. I feel like I should know, but it's just not clicking for me right now. Is we get x plus 1 to the fourth at the bottom for the denominator.
Oh, because it is. Remember the rule says the denominator square. Remember that's what the quotient rule says. The denominator square. Do you remember that?
Oh, okay, right.
So since I already have a square there in the denominator, I have to square it again.
Okay,
So
and then
what-
it cancels from the one up top there. Okay.
Right. So sorry, I was going to do that there. Right. So it's going to be the denominator square. So it's going to be square. So that's where I get to the fourth power. And then this one cancels with one of them inside here. So we have it to the third power. You got that?
Yes, sir.
All right, good. And then now, when I get this answer, I'm going to substitute 0 into it. So it's going to have 0. And remember the question that I preempt what Daniel was asking? Don't think that is going to be 2 over 0. 0 plus 1 is 1, and 1 cube is 1. So you have 2 over 1, which is 2. The third derivative is going to be following from the second. I'm differentiating here. Watch me. The denominator, see here, times the differentiation of the numerator, differentiating 2, is a constant, so it's going to become 0. Minus numerator, minus this 2, see here, boom. Times the differentiation of the denominator. Now the denominator is a power. So it's going to become 3 in front, see here, so, times this x plus 1 to the second power, see right here, so, and then times the differential of the inside here. So when I differentiate x plus 1, I'm going to get 1, see right here, so. All over the denominator square. So it's going to be x plus 1 to the third power square. So it becomes x plus 1 to the 6. See it right here, so. All right. This 0 times everything here gives me 0. What negative 2 times 3 is negative 6. Negative 6 times 1 is negative 6. So I have a negative 6 up here. But best believe that this x plus 1 all square is going to cancel fully into x plus 1 to the 6, leaving 4. That's why the 4 right here. And again, when x equals 0, 0 plus 1 is 1. And 1 to the 4th is 4. So we have negative 6 over 1, which is simply negative 6. I know it's 9 o'clock, but I want to finish off this thing. I'm just going to ask for 5 more minutes. Nestor, you're going to sleep. Nestor, you're going to sleep. Nestor, wake up.
No, sir.
All right, good job. All right, so look at this now. I am not going to go through the fourth one. I want you to quickly do the fourth one and tell me if you agree with this 24. I'm stepping away for 2 minutes, stepping away for 2 minutes. And when I come back, I want you to tell me that you, matter of fact, I can walk with the device. Look at it and tell me what it is that you have. I'm walking with the device. Look at it and tell me what you have. Mute, Ottilie, mute.
I had stepped away. What did you ask us to do something?
Now, I was just saying that, yeah, I want you to check to see if the fourth derivative, if you agree that the fourth derivative is what it is, and if when you substitute 0, you got the 24 like I did. But I was hearing some talking in the background, so I was saying to you to mute. But yeah, just double check the fourth derivative that I have. As I said before, it don't make sense. I just run through the question and you don't get an opportunity to put pen to paper and do it. The aim is for you to do it and understand it. So I project the answer, you just double check until if you agree with what I have. Come talk to me now. We get it?
Yes, sir, I got it. I ran through it in my head.
Nice job. Nice job. So it's the denominator times the differentiation of the numerator. The numerator is a constant, so it becomes 0, minus the numerator is -6, see here, so, times the differentiation of the denominator. The power rule. So it's going to be 4 in front, see it right here, so, x plus 1 to the third times the differential of the inside, which is going to be 1. This square is going to be, remember, no, this square is going to be 4 times 2 to give me 8.
8.
Right. And then all of this is going to be 0 in blue. And -1 times -6 is +6. And 6 times 4 is 24. Times 1 is still 24. That's why I have +24 here. And all of this x plus 3 will cancel into this and leave 5. And I substitute 0. 1 to the 5th is still 1.
Sorry, go again with the 5. Come in. Sorry, go again with the 5. Make you didn't add
X plus 1 to the 3rd. When I cancel it into this here,
definitely.
I'm gonna get 5. 5
right,
left.
okay, get it. This time I lose it. That's where I got lost with your answer.
Sir, and what's the reason you said the 0 doesn't become 1 in the denominator again, since it's x plus 1? What's the reason you gave for Daniel's confusion?
Because 0 plus 1 is 1. And 1 to the 5th is still 1. So in a case
okay, so it would be
right. So in a case
24 over 1.
Right. And put it this way. Put it this way, Papa. You won't have the denominator become 0. Because the denominator becomes 0, you have to stop the question because you can't continue. Yeah, don't it?
Yeah.
And it don't make sense when you want question but can't work. You start on first piece and you can't go to the second piece. It means there's a full question that. All right, so that is that. And then the final piece now is me differentiating the 4th derivative to get the 5th one. So why do I have to go all the way to the 5th one? It says up to and including the term x to the 5th. So I have to do the 5th one. Watch me. The denominator, see here, x plus 1 to the 5th, boom. Times the differentiation of the numerator. When I differentiate the numerator 24, I get 0, boom. Minus numerator is minus 24, see here so. Times the differentiation of the denominator. It's a power rule. 5 goes here, see it here. Times the different, and I'm going to reduce this by 1. So it's going to be x plus 1 to the 4th. See it here. And then now times the differential of the inside. When I differentiate x plus 1, I'm going to get 1 over the denominator square. Please, when the question was asked of me just now, I don't want anybody to think, when I answer, I don't want anybody to think that I'm going to square the 5 to get 25. It's going to give me 10. Because when I have a power, raised to another power, I multiply both powers. So 5 here so, and I square with that 2. 5 times 2 is going to give me this 10. All right. Now all of this go to 0. 24 times 5 is 120. Then negative 120 times 1 is still negative 120. See here, so boom. And then I'm going to have 1 x plus 1 to the 4th. All of this can go into all of this. Sir, how you know? Because up here only 4 and only a 10. So all of this going to all of this, and we have 6 left. See it right here, so. And substituting 0 into the function, 0 plus 1 is 1. 1 to the 6 is 1. So you can have negative 120 over 1, negative 120. And then finally, and I'm going to send this off to you so that you can look at it. Finally, and then maybe give you 1 for homework. Finally, I have a formula. That formula is taken from this up here. So it's the same formula copied on here so that you can see what is happening. Look at what I'm doing. F of 0 is 1. I substitute the 1 right here. So f dash of 0 is negative 1. I'll put the negative 1. But remember, set up 1x here, so it will become negative 1x. See it right here, so boom. Then I move f double dash of 0. F double dash of 0 is 2. So I'm going to have 2 over this 2 factorial. See it here, so boom, times x squared. So you can see that I'm going to substitute my f, the values that I do over here. Then this one is when f triple dash of 0. F triple dash is negative 6. So it's going to be negative 6 over 3 factorial times x cubed. See it right here, so boom. The next one is going to be 24 plus 24. You know that it's recognized that the signs alternate. It starts off with a positive, then it goes to a negative, then it goes to a positive, then it goes to a negative, then it goes back to a positive. So I'm at 24 now. So it's going to be 24 over 4 factorial because this is f to the 4th. So it's going to become 24 over 4 factorial x to the 4th. And then to the 5th now, it's going to be negative 120 over x to the 5th, over 5 factorial, sorry, times x to the 5th. Plus, and I'm not going no further because them say must stop right here, so. Them say must stop right here, so. And when I evaluate this one, that one is 1. Negative 1x is just the same thing as negative x. But 2 factorial is 2. So 2 over 2 is 1. 1 times x squared is x squared. 3 factorial is 6. So 6 over 6 is 1. So we're going to have negative x cubed right here. 4 factorial is 24. So 24 divided by 24 is 1. So we're going to have 1 times x to the 4th is just x to the 4th. And guess what? We already evaluated 5 factorial at the top of the class. And we know that 5 factorial is 120. So 120 divided by 120 is simply 1. So this is just negative x to the 5th. Boom. Question finished. It's long and tedious, but you get the marks for it. A question like this again can come anywhere between 5 and 10 marks.
You're giving us some marks on this?
I will. I'm just going to generate some questions and send off to you tonight. I definitely will.
Okay.
All right. I'm going to end here. Get some rest. Do some light work. And if you can get up early o'clock tomorrow, you have to start putting in the work now, guys. You must put in the work now. All right. I don't think all of you have access to Edico yet. It's just a few of you. If you don't have access to Edico, just drop me something in the WhatsApp group now, please. And then I'll add you a little later. Just again, cool off a little bit and then get up and do some work. Because I have a class tomorrow morning. Wow. But never mind.
They're the same password?
It would be. It would be.
Okay.
Yeah, man.
Yeah.
All right. All the best, guys. Take care.